This class is going to be divided into two things. The first thing that we'll do right now is a lecture, which is going to be about how neural networks are trained, so aka the backward pass. Last week was all about the forward pass. This week we'll talk about the backward pass. And then the interactive machine learning. That's kind of a continuation of the practical stuff that we did from the practical stuff that we started last week. We're going to introduce some new tools that you'll have at your disposal. This is kind of like one of my favorite lectures to give because well, there's a certain beauty, right? I think aesthetically to the way that these neural networks are trained, because it's really improbable that you can optimize tens of millions of numbers at the same time, and so there's a lot of creativity that went into figuring out how to do that. And it's also, I think, a difficult lecture to give because in this context, in this sort of artistic creative context, there's a continuous conflict between two goals. One is comprehension, and one is abstraction. And if we're in, let's say, a computer science class, we may not be so concerned by that because we're just trying to go for comprehension. But here, there's a lot of the deep down stuff is not necessarily, we're kind of higher up the stack, let's say. And so we're not necessarily concerned with some of the underlying math. However, there's actually, besides for the just interest in it for its own sake, there's actually a lot of practical value to understanding these. Because later on, when you might be, let's say, training a GAN or something, and they're notoriously unstable, and you might be able to actually kind of diagnose problems that in the training process that you're unaware of. And another thing is, in general, it helps you to understand how these things can be kind of combined and recombined. And so there's actually a lot of practical value in knowing this stuff. So. Just a few items before we begin, some announcements. So this, just 2 days ago, speak of the devil, we were talking about 3D data sets, and just 2 days ago, lo and behold, the biggest one ever, pretty much, that I'm aware of. It's not exactly a 3D data set in the sense that there's no, it doesn't come with as far as I know, meshes or voxels. But it basically is comes from 1 million CAD images from real production of interior data sets, interior scenes, and then decomposed into 22 million images, individual images of of the layouts, right? And it comes with all this value-added content. So there's the texture, there's the depth and the normals. So you have the ability to reconstruct 3D. It has multiple views, and it has a semantic map. So all of the different categories of objects are labeled. And so for those who are interested in 3D, my understanding is that maybe the license is kind of restrictive, and it may not be a necessarily very easy data set to use, but just in general, if you're interested in 3D, it's worth maybe investigating. Another item I want to announce is, so Chris and Alejandro are going to be here. Oh, so this is what we announced. That's Chris and Alejandro. I'm going to pause this because let's actually pause that. Yeah. So we kind of hatched this idea so just recall that after next week, is it? Yeah, week 4. We're going to have a gap of 2 weeks. One is a scheduled week where you don't have Tuesday classes, and it's just a Monday class on Tuesdays. And then the week before, October 2nd, I'm actually out of town. And so we hatched this idea for Chris and Alejandro to do an additional session. It's not a makeup session. It's actually just an extra session. So this is the other end of the bargain for having a class where people couldn't get in. You just have to go to this. Yeah. So I'm just kidding. I can't compel you to go to an extra class, but this will just be for your benefit, and it should actually be really cool because Chris and Alejandro are going to demo the alpha version that they're working on, or the beta version rather, I suppose the alpha of the beta. They're going to show you the unreleased runway and actually give you, distribute basically copies of it. So you'll be the first beta testers. It'll be very valuable for them because you'll get to try to break it for them and kind of give them feedback. And then also you're going to have this really powerful tool on your plate because Runway is really awesome. Just the alpha version I've been using in a lot of workshops, and it's going to very much up the amount of things that we can do. And so this will be really, really valuable. You'll be able to do amazing projects with Runway with very easy setup and so on. So I very much encourage everyone to attend this. It's going to be during the normal hours, and we'll announce more details closer to the date. We just came up with this yesterday, so there's kind of more details to be determined. Okay, and office hours. So I still haven't done something formal. My apologies for that. But basically, like for this week, let's just say that my office hours are all day tomorrow. Like I'll be here all day, and so if you want to make an appointment, just email me, and I'll make some sort of a calendar functionality at some point soon. The asterisk is Wednesday really includes Thursday and Friday because I'm here every day more or less, and so if you have classes all day on Wednesday and you can't make it, just email me and we'll just arrange something on Thursday and Friday. I may not be here the whole day for all of those, and so just email me in advance and we'll figure that out. So that's office hours, and then hopefully in the next few days I'll have something like a calendar app. Okay, let's talk about how neural networks are trained. Yeah. So last week in the first 2 sessions we kind of introduced the supervised learning pipeline, and we talked about how well, we mostly focused on the bottom part of this, right? The function that fits some input data X and maps out to some output data Y. And we talked about a lot of different ways of using this and a lot of different cool applications. But we really sort of glossed over the top part of this, the learning algorithm and the training data, instead preferring to look at it as basically like a form of magic, right? As sort of evidenced by this like blue wizard man. That's the sort of way that we normally like to think of this function, right? It's just sort of like magic. I should really stop putting my slides together so late at night. Okay. So in the context of image classification, right, we are usually unfolding images as pixels into neural networks, right? So we kind of take the input data, the raw media, let's say, and use that as an input to the neural net. And the neural net is characterized by these, this is just a review of last week, right? Neural net is characterized by these neurons, these units, that have very simple operations. They just sort of add the signals that they receive, a sort of weighted sum, and then they go through some nonlinearity, which is usually like this ReLU function, right? Which is just a max. So a neural network, just to get the gist of it, right? A neural network is basically characterized by neurons / activations, right? The values inside the neurons, and all of these mathematical operations, which are indicated by these connections, right? So these connections all have weights, and you know, there's various like metaphors that you can use to kind of have this in your head. I often think of like sort of like a signal, like something like an electrical signal, or maybe water. People like to think of water traveling through pipes, and the weights kind of is like the resistance, or you know, that let in a certain amount of signal. So you can think of it that way. And but the important thing is, if you forget all of the operations, like the actual math inside of them, the most critical thing to understand is that the input to output mapping, that relationship, is entirely characterized by the values of the weights, right, or the parameters, right? We call them weights or parameters, and there's many of them, right? They're all on these connections, right? And depending on what combination of weights you set, you have a unique shape to that function. So, and we saw a hint of this, right? That when we actually train, it's sort of this iterative process where things are trained iteratively. The weights make very small updates, and then they converge on some representation of the data set, which is useful for you know, analytics, right? And we kind of saw this coming through in this visualization, right? And we talked about how in a 2-layer neural network you can form like a compositional hierarchy of features. In the first layer, maybe you get things like let's say in the context of numbers, you get strokes or loops, or you know, parallel lines, things like basic features, and then you kind of combine them in the second layer, these sort of low-level features, into higher-level features, like combinations of loops, combinations of lines, to recover the actual shapes that we're interested in, right? And then we also introduced convolutional neural networks, which are basically neural networks that have convolutional layers. And convolutional layers allow us to do this a little bit more flexibly, because we have these sort of small filters that are able to scan across the entire image and locate a particular feature all over it, right? And this is kind of repetition, because then we are able to we're able to get many features, but for a very small amount of weights. And this kind of gives us some efficiency as well. And that was kind of like, that was the basic gist of it. And you can look at this process a little bit more closely using the ConvNet viewer, which comes with ML4AOFX. So, so now let's talk about how training actually works. Now, before we do that, let's actually try to appreciate just what makes it so difficult in the first place, right? The first thing to observe is that the weights, the parameters, are not linearly independent. In other words, one weight, let's say in the first layer, actually affects all of the subsequent layers downstream, right? Because it affects this neuron, the output of this neuron, and so this changes all of these signals and then downstream. Yeah?
Why wouldn't it also affect all the weights to that neuron that it's connected to in the first layer?
Which one? This one, this connection is changing, right?
Yeah, so but so do the weights not like sum up to 1 always, like for a given neuron?
No,
necessarily?
no.
It's like arbitrary, so we
they
don't
do not
have to
sum up to
readjust
weight.
either.
Yeah, yeah.
Right, okay.
So it affects all of the weights downstream, and there's actually like, this is a sort of simplified version of this, but the point is that the weights cannot be set one at a time. We can't optimize them individually. It's not like each weight has a particular optimal value. It's that there's a global combination of weights that gives us optimal behavior, right? So, so then let's take a simple approach, like a naive approach, right? What's a naive approach to optimizing the weights? Well, how about random guessing, right? So let's, random guesses would be like, you know, computers are very fast, so we can just set the weights randomly and see what the loss is, see what the error is, and then keep the and then do this many times and then keep the combination of weights that performs really well. Well, the problem with this the problem becomes clear when we consider the sort of search space of all possible random weights, right? So suppose you have just 2 parameters to optimize for, 2 weights. You have like a really simple neural network. Well, let's say you want to sample the space densely, right? You want to be sure that you have checked every possible, you know, not every possible, but a good percentage of all the possible areas of the search space. So you might kind of take each of those parameters and divide them into 10 buckets, right? Like a precision of 10% basically, and then try each of those, right? So if you have 2 parameters, that means that you would have 10 weights for each, 10 values that you want to try for each one, and then therefore 10 times 10 equals 100. We have 100 combinations of weights. Not so bad, right? Let's say we have 3 weights. Well, then it's going to be, it's like a cube, right? It's going to be 10 times 10 times 10. That's 1,000 weights. So it should become pretty clear what the problem with this is, right? The more weights we have, we are exploding our search space exponentially, right? And in like a simple neural network, like the first fully connected neural network that we looked at last week, MNIST, right, which looked like this, we would have, let's see, 784 pixels. So there's 784 neurons here, times 10 middle inputs, right? So we have, computer's very slow, times 10 plus 10 times 10. So we would have roughly, oh, good God. I really need a new computer. My God, it's really, really bad. We have roughly 8,000 parameters to optimize for, right? Which is quite a lot, obviously. Yeah, there it is. 8,000 parameters to optimize for. Now that's still not so many. Like you could almost optimize that randomly. Like, you know, you can make hundreds of thousands of guesses, right? And you'll do like a bad but sort of like plausible job. But consider the fact that a modern neural network, to get the kind of accuracy that we need, often has in the tens of millions of neurons and the hundreds of millions of parameters, connections, right? Which is somewhere similar to frog brains, I'm told. So that's roughly equivalent to a frog brain. But it's actually, frog brains are still more complicated because frog brains have neurons, biological neurons have all sorts of capabilities that we don't actually model. So they can delay their signals, they can they can fire in a sort of, in a nonlinear way, let's say. They're not arranged in layers necessarily. Like we're very strict about having layers because it's convenient for computation, right? So this is still not approaching the complexity of a frog brain. And of course, like complexity of a human brain is several orders of magnitude above that. So a human brain has roughly the hundreds of billions of neurons and hundreds of trillions of connections, weights, right? So, but even still, with a modern convolutional neural network, we have hundreds of millions of parameters to optimize, which means that the search space is like inconceivably large. And just to give you a sense of the scale, the number of grains of sand on Earth is a 20-digit number. The number of atoms in the universe is an 80-digit number. And if we take AlexNet, which was like the first really successful convolutional neural network, to sample that to 10% precision, that would be the number of weight combinations we have to try is a 62 million digit number. Okay, so pretty difficult to optimize. You can take all the computers in the world and like leave them running until the end of time just to solve it, and we won't even come close, right? So obviously we need something more efficient. So the way that we're going to introduce that more efficient method is to actually start with a very simple method and scale it up. We're going to add some complexity to this as we go. Linear regression is actually something that many of you probably learned about in grade school, right? Like you kind of learned this in introductory statistics class, or maybe like introductory, I don't even remember anymore, like maybe linear algebra or calculus. And the task is you get a line, you get a set of points in 2D, and you're trying to fit a line, y equals mx plus b, right? So try to fit a line. You can kind of see that like a line that roughly looks like where my mouse is moving is probably going to be the line of best fit, right? Something like that. Now, like suppose we just try 3 random lines, right? So here's 3 lines I've given you to try to fit those to fit this chart. Now, pretty clearly, the second one looks pretty bad. The first and the third look like plausible, and this, maybe it's kind of hard to tell which one is the best. Now, how do we actually evaluate which one is the best? So we need some sort of a loss function, a function to evaluate the error or the inaccuracy, right? And for regression, let's say we can use what's called sum squared error or mean squared error, right, which are closely related. And what it is basically you take the error bars, the predicted value and the actual value of those points, given the line that you fit through them, and you square them and you add them, right? So that's what all this equation is. J is basically the amount of error, and it's the sum of the squared error bars, right? And you might see mean squared error, which then averages over the amount of points, but it doesn't really matter because that's just like a linear like multiplier. The point is that the more the sum squared errors are, the higher your error is. And this 1/2 is just for convenience sake. Like it's actually it's just for convenience when we actually take the derivative, as you'll see in a moment. It doesn't really matter. You don't have to worry about that. So people might think like, why not use just the raw error bars and then add them, or the absolute value? And there's kind of multiple reasons for that. One is that we want to penalize large deviations more. So when you square large numbers, they're proportionately even bigger. And then the second error is that it's like not super, like having absolute values and things that you're taking derivatives of gets complicated. So you typically see mean squared error. It has like a nice theoretical formulation. So, and then, okay, this might be a little bit TMI, but I just want to include it. For classification, we actually don't use mean squared error. We usually use something like cross entropy, and which I'll get to in a minute. So there's one more activation, which you'll often see. And again, don't worry too much about the mathematical formulation of this, because it's not super necessary for us, but kind of just for the sake of completeness, I'm including the slide here. We use what's called a softmax activation, and the formula of that is given below. That's very often used as the output activation for a classification. And the reason it's used is because it has a nice, like, it's basically interpreted like a probability. So when you get classes at the end, you can, because the number bars are sort of unbounded, and they don't really have any like justification. So we can actually like map them through a softmax, and which is given by this, just e, like exponential, and then they add up to 1 at the end. And we don't usually use as an error bar. As an error measure, we don't use sum squared error or mean squared error for classification, because it doesn't really make sense exactly, like because classification is sort of on or off, and so measuring like an error bar is sort of like doesn't really make sense in the context of classification. And instead, what's usually used is something called categorical cross entropy, The justification for this is super complicated, and it's like information theory, and it's super interesting, and you can look it up. But it's not. It doesn't really matter for us. The point is just know that you might see this sometimes, categorical cross entropy. And the important thing to understand is that if our predicted values are roughly approaching the actual values, then the loss actually goes down to 0. You can see this in this example. But okay, don't worry about calculating that. And then it actually goes to infinity as we approach something wrong. Okay, so now let's think about the cost function, right? Now suppose we have this linear regression, right? And we have all of these different values of m and b that we could have, yeah. Then we can actually look at what the cost function looks like. We could graph it, right? So for a linear regression, it's a quadratic. The cost is a quadratic function because of the squared, right? And so for every value of m or b, you'll have a point here that reflects the cost, and it's always going to be ball-shaped in linear regression. This is called convexity. It's a convex function, and so we can kind of see what we're trying to do. Like you can see visually that we're trying to find the value of m and b, which is at the bottom of this bowl, right? And you can kind of see that it's like roughly m equals 1, b equals 0.5, something like that. Yeah.
Does cost mean error here?
Yeah.
Okay.
Cost and error are synonymous. Yeah. So we're trying to get here. Now, obviously, like if we can just graph the function, we can just calculate it analytically. Like we calculated all these error bars, right? So it doesn't. So it's a little like contradictory that we're trying to find an unknown value that I've graphed for you. But the point is that you won't actually be able to do this with a neural network to calculate all the values in advance for the reasons that we just explained just a second ago. But this just gives you like visually what that actually looks like, right? So we're trying to get to the bottom of this. So what's one way of getting to the bottom, right? Now, this is where like if a mathematician were sitting here, they'd be like, what are you doing? Like you wouldn't use the method that I'm about to show you to solve linear regression, because linear regression can be solved analytically. Like you can solve it with a paper and a pen. But you can't do that with neural networks. With neural networks, you have to use a technique called gradient descent, which I'm going to introduce. So I'm going to introduce gradient descent in the context of linear regression because it's very simple to understand. And then we'll apply it to neural networks. So here's the method in a nutshell. You pick a random point, right? Like you pick some random point like that is your initialization, and then you calculate the gradient, what's called the gradient. Now get used to hearing gradient because in machine learning you hear gradient all the time. So it's important to understand what it is. Gradient is basically, in mathematical terms, it's just a generalization of a slope in multiple dimensions, right? So a slope for a parabola, right, is like the instantaneous rise or fall that it's going in a graph, right? Everyone learns slope. So a gradient is, let's say you have a function of 2 variables, then it's a vector which contains the partial derivative of each of those functions, like with respect to each dimension. So here we have 2 parameters, m and b, and so the gradient is basically a vector that relates the slope of our function, which is j, right, with respect to each parameter. So it's slope in 2D, right? It's a like the best way to think of it is, or slope in multiple dimensions. The best way to think of it is it just gives us, for any point, it tells us which direction is it going. Is it rising or falling, or is it, which direction is that surface going, right? And knowing that information, we can take the following algorithm to find ourselves the optimal solution. We would pick a random point, let's say, calculate the gradient, and then go down the gradient, right? Like we want to change the parameters in the direction such that j diminishes the most, right? So if you calculate the gradient, you have this vector it's actually pointing upward, and so you can go in the opposite direction by some amount. We take some step, right, in that direction. And then we keep on doing this over and over and over iteratively until we get to the bottom of the bowl, right? And then once it stops declining, we can basically stop. We found our lowest point, and so this is the optimal solution. And these are like the update equations. Now this little alpha here denotes how big of a step do you take, right? And this is usually what's called a hyperparameter. And that's something we'll talk about later. But hyperparameters are things that have to be chosen by the machine learning scientists. And if you choose too big of a learning rate, it's called the learning rate. That's another way of calling it. It's like the rate at which we learn. And if you update it too much, then you might overshoot. Like you might go too far. If you update it too little, then you might it might take too long, right? So this is one of these things that has to be, there's kind of usually trade-offs to them. But the point is, in this general framework, we have this update rule that we apply iteratively where we change the parameters, M and B, by adding their gradient, by adding like each element of the gradient to them until we get to the bottom of the bowl, right, roughly speaking. So this can actually be calculated, and I'll leave this as like, again, for completeness sake, this is in the slides, but we're not actually going to go through the proof. So like, but if you've learned like basic calculus, you can actually do this relatively quickly. The point is that if you do a little bit of calculus, you can actually get a function which tells you a way to calculate the gradient. To calculate each element of the gradient is basically a function of the parameters themselves, right? So you have this function that you can use to calculate the gradient, and so now we have a method by which we can compute. And I'm going to release at some point a Python notebook that lets you do this for anyone who's interested, like step by step, to actually see the values. You'll be able to do this. So, but the point is that basically if you apply this and then you measure the cost, then you calculate the gradient, and then you update the parameters with respect to the gradient, and then you do this over and over and over, and slowly your cost will decline. And that's how you know you're getting to the bottom of this bowl, right? Now, let's suppose instead of having one input neuron, we have two input neurons, right? So instead of M, we're going to change M to W. And W is actually, there's going to be like multiple W's, right? There's a W here, W1, and a W2. Then you have a function it's a plane, right? So if there was just one of these, it would be W1 x1 plus B, that's a line. And W1 x1 plus W2 x2 plus B, that's a plane, right? So that's all it is. It's like analogous to a line. So suppose we have two inputs. Well then, it's exactly the same. You just end up having three elements in your gradient, right? Because there's three parameters that you have to solve for: W1, W2, and B. So now we have a gradient, which is a vector of the slope with respect to each of those parameters, W1, W2, and B. And the derivative is actually like very similar to the last one. You can do it as an exercise if you wish. But the point is that it's easy enough to do this for any number of points that are going into here. So you can still do linear regression with any number of variables. Now, here's the problem, and now where we're going to make things worse. So linear regression is a fine way of fitting functions of any number of variables. But the problem is that linear regression just doesn't work that well. And the problem with linear regression is that it's a line, right? It's really inflexible. So let's say you're trying to model data which actually is, you know, curved in some respect, or kind of like non-linearly distributed. And this is actually quite difficult to actually fit a plane through them without sacrificing a whole lot of accuracy. And so linear regression just turns out to be unsuitable. And so what we do is, as we introduced last week, we introduce a nonlinearity into the equation. Instead of just outputting the weighted sum, the plane, we will go through some activation function, or like a nonlinear activation function, like a sigmoid, or more commonly, and that's actually what a sigmoid looks like, by the way. It's not a plane anymore. It's a curved space. But more often we'll use ReLU, right? Rectified linear unit, which just means max operation, max of 0 and the value. And that makes the whole thing nonlinear. Which means, by the way, now that those equations that we derive for the partial derivatives, they don't apply anymore. Those were made for nonlinear regressions. The derivative with this nonlinearity changes. So, and now we're going to complicate things even more by adding more layers, right? So now we have a neural network, right? The difference between a linear regression and a neural network is nonlinear activation functions and set up in this sort of like sequence of layers, right? And that's kind of what we have here. We did a demo of this last week, right? So you can play with the demo, the forward pass demo online if you go to that link. So then how do we do gradient descent now for neural networks? Now, first I just want to point out, now it makes sense. Like, you don't do gradient descent for linear regression because you don't need to. You can actually calculate the optimal value. But for neural networks, you can't actually calculate the optimal value in advance. You have to do gradient descent. Well, there's other ways of solving neural networks, but basically gradient descent is the most popular way, and we're going to show how that works. So with gradient descent, we're still doing this basic idea of gradient descent. We have a loss function, like a loss surface, let's call it, and we want to find the bottom of it, right? So we can now use gradient descent, which involves taking all of these parameters and finding their gradient, right? Or finding the gradient with all these parameters. It's really coming down now, huh? Yeah. So we can, so gradient descent in this context would be finding a vector of all of the slopes of each of these parameters. And you see that there's like parameters in, there's now, how many? There's 3 times 2, 6, 9, plus 4 biases, so there's 13 parameters, right? So now the gradient here would be a vector with 13 elements, which is the slope of the loss function with respect to each individual parameter to optimize. So, like, what's one way of calculating the gradient, right? So we don't have a nice pretty function for it anymore. So how can we actually calculate the gradient? Well, one way of doing it is just using the original definition for a derivative. A derivative is just given by a limit, right? So we can, and in the context of the loss function, you would basically take each parameter. You would calculate what the loss is with respect to where you are right now. Then for each parameter, you would add a tiny bit to it, right? Like some little delta W. And then calculate the error again, and then divide it by the delta W. You'd calculate it by brute force, basically. Now, this works, right? This is basically like the classic method. But the problem is that it's super, it's really simple, but it would take too long, right? Because you have to calculate this J, you have to do a forward pass, like which is a lot of operations, and you have to do it for every single parameter that you have. So that might be hundreds of millions of them, right? So it's going to take a really, really long time to calculate the gradient. So this doesn't work, right? And this was the main bottleneck for training neural networks for a long time, because we've had this idea, like the basic equations have been around for 100 years, let's say, right? Like it's not like this, like the math we're using is more than 100 years old. But we couldn't figure out how to optimize these in a way that was reasonable for a really, really long time. And this is kind of like what we're going to get to. I think the next slide is backprop, right? Yes. Okay. So now we're not going to go into detail about backprop. I just want to tell you about it, right? Because backpropagation is like the miracle of the 20th century. That's really bombastic, but maybe like some people would say that's true. And backpropagation is a computational technique. You'll hear backprop a lot. Like usually people, when they talk about training neural networks, they talk about backprop, right? Backpropagation. And backpropagation is a technique for doing gradient descent in a way that's efficient and computationally effective. And we're not going to talk about it in detail because it's pretty complicated, right? Like humans only figured it out in 1986, let's say. Backpropagation has been derived multiple times by multiple people in multiple contexts, but the first person to apply it, because it's very similar to just any sort of multivariate optimization problem, but the first person to figure, or let's say the first team, Jeffrey Hinton and his collaborators, figured out how to apply it to neural networks in roughly the mid-'80s. And this was the first time that you could sort of use backpropagation to do gradient descent on neural networks and solve them, like to train them in a way that was efficient. Now, this was still a long time before we're hearing so much success, right? So like why wasn't this so successful back then, right? And the reasons why is because there were still problems that they had to solve, that they would go on to solve over the next 20 years. And also because neural networks in general are very, very like, their performance depends a lot on the amount of data. And so data sets back then were really small. So that's kind of mostly why it took a really long time. And so this was kind of a minority of computer scientists believed in neural networks and backpropagation, because and so like there were other methods that were kind of like dominant throughout the 90s and 2000s. And so it really took until literally like the last 5 to 7 years for these things to go mainstream. The idea of backprop in like in the highest level sense, and I don't really fully understand backprop myself, so like if you don't worry. There's really good reading about this, by the way. I'll publish the slides later, so you'll get these links. But that actually explain it I think a really sort of accessible way. But the idea of backprop is that we can calculate the gradient efficiently using the chain rule, and so people will get in fights about whether or not it's just using the chain rule. But like it's basically using the chain rule. So the chain rule, as you probably know in calculus, is a way of relating the derivative of a complex function or a composite function to the derivatives of each of its internal components. So if you can take a function and decompose it as like a function of a function of a function of a function, you can get a formula for its derivative by taking the derivative of each of those components, right? So like if you have and I'll actually have supplementary slides when I do the NumPy lesson later, so you'll see this in a little bit more detail. But that's the basic idea. And so with a neural network, you have this sort of sequence of computations that go through layers, and you can actually decompose that effect that it has on the loss into a big chain of functions, each of which and then you can decompose it into each individual like derivative. And so at the end, we get this value of the loss, and we can sort of backward propagate it, which means we take the loss and we go backwards through the network, and we sort of allocate the amount of the contribution to that overall derivative to each individual connection along the way, something like that. And the reason why it's very efficient, and this is the way that I think of it. I don't know if this is exactly correct, but it makes sense to me anyway. Like it relates the gradient to the activations as you calculate them. So it's actually like when you do a forward pass, you save all the activations, and then the amount to change the weights is then actually just related to the activations, like in a very convenient way. And so that means that you can do backprop in roughly the same amount of time that you can do a forward pass. And that's like many orders of magnitude faster than doing like computing the derivatives like one by one efficiently. Wow. So yeah.
Does it do backprop done all layers at the same time, or done layer by layer by layer?
It's done layer by layer. Like you basically go backwards through the network, and then yeah. I mean, well, like technically all of the weights get updated at the same time, but it's computed sort of sequentially. Yeah. Like the way it's implemented. Yeah. There's good reading about this that I highly encourage people to look at. Let's see how we're doing in time. Okay, pretty good. Okay, now here is the problem with neural networks, and basically like nonlinear multivariable functions in general. Now remember we were looking at the linear regression, and its loss surface is this nice smooth bowl, right? And we said it's convex. Convex means basically bowl shaped. Like there's no if you run a line through that surface, it'll at most intersect 2 points, right? It'll go inside the bowl and then outside. That's kind of what convex means. And convex means that if you look at the actual bowl, you're guaranteed to do, like if you do linear regression, if you do gradient descent on a convex surface, you're guaranteed to get to the bottom, because it will keep on going down until, man, these slides are, yeah, oops, going too far. It's guaranteed to get to the bottom, right? because wherever your initialization is, all roads point downhill, right? But in a neural network loss function, it's not at all this way. It's actually it's more shaped like an egg carton or something like that. Let's get back to that slide. Oh boy. So this is a huge problem, and and basically why training is so hard, right? Because what happens if you do naive, let's say, gradient descent on a loss function that is so complex, is that you're very likely to get stuck in what we call a local minimum, right, or a saddle point, right? So like we can see this in a second. Yeah, there it is, right? Like if you pick a random number or a random parameterization, and then you do gradient descent, what might happen is you might get stuck in like one of these valleys, right? The gradient stops pointing downward, and so you go, oh, I'm finished. This must be the lowest error, right? But it may not be, right? And in general, there's no way around this. Like we have lots of local minima, and the global minimum is like a needle in a haystack. It's like really, really difficult to find. And in general, like we don't have a way of finding the global minimum in a neural network effectively. We just have ways of finding good local minima. And the way that we try to solve this problem, I'm just going to give you sort of a high-level abstract view of this, because what's going to happen is that when you start to learn about training and you start to do training, and maybe you start to use frameworks like Keras, you're going to see a lot of jargon, like a lot of like technical terms about what the exact optimization objective is, or what the method for calculating the gradient is, and things of that sort. And this will give you a high-level view, a bird's-eye view of those things. And in general, they're just complications to standard gradient descent that try to solve this problem, mainly, of getting stuck in a valley, right? So one way of getting out of these valleys is, instead of calculating the gradient on the entire data set, you calculate the gradient on subsets of it. So if you calculate the gradient based on all of your data, right, which is to say you fit your function through all of the data, right? Like when we did linear regression, we fit the line through all of the data, right? If you do this for all of your data, it's called batch gradient descent, right? And in general, almost never is batch gradient descent used. In practice, what's used is either stochastic or mini-batch gradient descent. And just, by the way, it's a little confusing because sometimes people use those terms interchangeably. So there's a little context there. But stochastic, as far as I understand it, stochastic gradient descent means you just pick a random sample and you calculate the gradient with respect to that one sample in the data set. And it ends up being that the reason why this kind of works around getting out of these local minima, you can kind of imagine like the local minima might change depending on which sample you use. Like the surface actually might change. And so like the way that your parameter updates go, it might be very, very sort of jagged. And it kind of like, you can imagine almost like a ball rolling down the hill, but it's really, really like bouncy. And so it might just basically bounce over a little valley, maybe go up a tiny hill and keep going down. And so that kind of works. Now, between batch gradient descent and stochastic gradient descent, there's mini-batch gradient descent. And this is typically what's used. Like almost always, most of the time, gradient descent is done in mini-batches, which means you take your data set and you divide it into subsets, like let's say of 60 samples or 100 samples or 200 samples. They're very often powers of 2, so you'll see like 8, 16, 64, so on. And then you calculate the gradient with respect to that. And that's kind of best of both worlds. So it's a little bit smoother, like batch gradient descent, but it still has enough variability that you can get out of these little valleys in the loss surface. And as a bonus, it's more computationally efficient because you don't have to forward prop all of the data, which takes longer. So that's kind of a nice feature as well. So that's one thing. So that's when you'll see mini batch gradient descent and stochastic gradient descent. That usually that's what they mean. In Keras, for example, like mini batch gradient descent is actually called SGD. So it can be a little bit a little confusing, but basically the strict uses of those terms means that. Now, just very quickly, like at a very high level, I want to tell you about a few other things in research. And these are things that have occurred over the last 5 to 7 years or so. I think something like that. And so they're just kind of worth being aware of. And we're not, again, I'm going to show links at the end that talk about these things in much more detail, including on ML4A. So for anyone who's interested in really diving into this, and I very much encourage you to, there are explanations that are a little deeper than I'm going to go into in this lecture, including ones in ML4A. Now, I'm just going to try to give you the sort of gist of it, and also try to, instead of like looking at equations, I'm going to try to give you the interpretation that I think works really well. So another way of getting out of these valleys is to use momentum. So what is momentum, right? Like we have an intuition for what momentum is. When you roll a ball down a hill, it has some, and it stops, and let's say you roll the ball down the hill and it gets to the bottom of it, and now there's no more slope, but the ball keeps on rolling anyway, right? So in normal gradient descent, the ball would stop, right? Because we're only moving it according to what the slope is. But if we let this speed sort of like decay slowly, that it has some memory, and that decays slowly, we give the weight, the update rule, some momentum. And so if you get to the bottom of a valley, you might be able to kind of roll out of it and then down into the next valley, right? So that's the basic idea of momentum, and it actually works very similar to, like, I always think of it like lerp in processing or in P5, right? So if you want to ease parameters, you can make things move smoothly. It kind of works like that, and you can investigate these equations if you wish. There's again, it'll be on the ML4A reading, but that's more or less what these equations give you. And then there's also, this might already be getting into TMI, but it's also a good opportunity to link you to CS231N, which is a class offered by Stanford. This is like the introductory computer vision course at Stanford using neural networks, and it actually goes into all of this stuff in way more detail. I highly recommend this class. It's really well done. The original one was taught and put online by Andrei Karpathy and Fei Li, who you may recognize these names. Now it's being taught by basically their original grad students. And Nestor of momentum is like a version of, so there's flavors of momentum, basically. And this is the kind of stuff that, like, getting really deep into the research, you'll encounter more and more. Nestor of momentum is like a little bit more of a natural momentum because it tries to calculate the gradient not where you are, but where you're going, right? So there's kind of this look ahead idea. That's the way I think of it. There's also a number of adaptive methods. So again, you're going to see these terms, like if you use Keras, TensorFlow, you're going to see AdaGrad, AdaDelta, RMS prop, Atom. These are all terms that denote like different flavors of gradient descent. And these four are a family of what we call adaptive methods. And adaptive methods actually change their learning rate, adapt like themselves. So instead of you choosing the learning rate, like how far it shoots, it actually tries to calculate it itself based on the history of previous gradients. So there's a momentum component to it, but it's basically adapting its own learning rate. This is a nice animation made by Alec Radford, which shows like optimizing each of these and what some of them may look like, right? So you can see, like, okay, like if you look at them, that's where we're trying to go. Some of them converge a little bit faster. Some of them converge a little bit more reliably. In general, there's really sort of like a lot of it, comes down to like trial and error. The rule that I'll give you, like for the machine learning for engineer rule, is when in doubt, use Atom. Yeah, it's basically because Atom is kind of the most modern method, and it kind of combines all of these things together. I forget what Atom stands for. It's like adaptive. Does anybody know? Anyway, like it's kind of when in doubt, use Atom. That's going to be like if you are given a choice, use Atom. That's kind of the best. Okay, so a few other components to understand about neural networks. Overfitting, right? We mentioned overfitting briefly last week. Overfitting is kind of visually given, and actually the Wikipedia page has a nice explanation of overfitting. Suppose we're given a set of points, these points right here, and we're asked to fit a function through them, right? And the whole point is to fit the function that is responsible for making that data set, right? Now, you can, if you want to, create an arbitrarily complicated function which perfectly goes through all of the points, right? You can see that this function, the really curvy one, has 0 error. It has 0 error, right? And whereas this line that kind of goes roughly through the points has some error, but it's way simpler, right? Well, you can imagine that, like, let's say these are all observations of some actual natural function, right? And there's some noise in it, right? So it's much more likely that this line, right, even though it doesn't have 0 error, is much more closely approximates the actual function we're trying to learn, right? Because and usually the rule is simplicity, right? Occam's razor, I think, is the kind of like philosophical rule. Like, when in doubt, make things as simple as possible. Like, explain the most amount of the data with the simplest possible model, and that in general is good because we expect it generalizes better. It'll find unknown points better. You can overfit, which means you create an arbitrarily complex function which goes through the training set perfectly. But guess what? When we give it unknown points, it'll probably be way off, right? Because like this sort of curvature is very unnatural. Yeah?
Can you give an example of what overfitting looks like when you're dealing with a specific kind of machine learning data set?
Sure. So for example, let's say you're training these, when we do generative models later, we'll talk about GANs and autoencoders. We train generative models to make, to produce models, to produce images that look like it came from a data set. Overfitting would mean that it just produces carbon copies of images in the data set, right? So it's overfit to the data set. It produces literally faces that are, let's say it's trained on faces, it produces faces that were in the original data set. So it's kind of useless because, well, we don't need a whole neural network to reproduce things that are already in the data set. It doesn't produce new things. So that's, in that context, overfitting. And in general, like, let's say you're trying to fit some predictive line. What happens in overfitting is that the neural network may tell you that you have a very low loss with respect to the training set, but then when you try to predict new samples, like unknown samples in your test set, it's actually way off, right? So there's kind of a big asymmetry between the error on the training set and the error on the test set. So that's kind of overfitting in the practical scenario. Yeah, good question. Now, how do we deal with overfitting? Because, you know, when you train a neural network, neural networks, of course, like, are extremely flexible, so they can become arbitrarily complicated shapes, right? And there's several ways of combating this, and this is, again, all terminology that you're going to hear when you read about this stuff. So one way is to use what's called regularization. And regularization roughly means basically adding additional objectives to your training process besides for just lowering the loss, right? So one such objective might be to keep the weights small, to keep their absolute values small. Because if you, like, and this is kind of like a little bit hard to explain why, but if the weights are relatively small to each other, or let's say constrained to like relatively roughly the same range, then you prevent huge fluctuations in the shape of a function, like huge fluctuations that look like this, right? And so one way of coaxing the network into regularizing effectively is to add a penalty term. So instead of just having raw mean squared error or raw cross entropy, we add this like regularization term to the loss, which, let's say, penalizes large values of the weights. Like, we actually just add a loss to the loss term, like the bigger the weights are, the bigger that this is. And so if we add it to the loss and it's trying to optimize the loss, it now has to kind of like negotiate between trying to minimize the the raw error and minimizing like the sum of the actual magnitudes of the parameters. So this is called, this is one form of regularization. It's called L2 regularization. L1 regularization would just be like if we had, instead of squares, we would have absolute values. And L3 would be cubes and so on. So that's kind of like, but usually you'll see L2. Another way, a much more elegant way, and a very new way, this is actually from 2014, and it's really cool. And it was come up with Jeffrey Hinton, the same person who came up with, who figured out backprop. So this guy's a big name in the field. is a method called dropout. And dropout is really cool. So basically in dropout, when you update the weights, when you update the parameters, like at each pass, you randomly select some percentage of them to not update. Like you just randomly select them and then you don't update them. And then at every pass through the network, it just like drops out randomly some subset of the neurons, different ones every time. And it's kind of a trick, but it turns out that this works well, and you can kind of you can kind of reason your way through it. Like to me, it makes sense because the network sort of like can't learn to depend too much on certain neurons that it favors, and this probably also has a little bit of an L2 regularization effect where it doesn't like the weight doesn't spin out of control because it doesn't get updated all the time. But this is a way of like making the network make the network a little bit more resilient to having some parts of the information like gone at some points. This is kind of cool because there's this whole family of techniques that involve like trying to like constrain the network artificially in ways that give it certain desirable properties. Like for example, when we looked at autoencoders, like what is an autoencoder? It constrains the network in a really, really like arbitrary way where we have some bottleneck layer. And then and it turns out that doing so has some really interesting like use cases for us. But it's constraining the network, right, in a way that like seems arbitrary and mean, kind of like, well, mean to me. Okay, so like that was the gist of it. That was how neural networks are trained. And I just want to note two things. One is that all of this was done very fast. Like I know probably a lot of it kind of went over people's heads. But I hope that like this first pass through it, we're sort of backpropping through understanding neural networks. Like we give it like a overall high level understanding of it. And then next time you can actually like look through some of these reading sources, they're like including ML4A, which is kind of this lecture but longer, and then also by other people. Like there's really good reading about these. I highly encourage actually the last link. This is written by Michael Nielsen, who's a really lucid writer, like excellent writer, and explains neural networks, their functioning like very rigorously, but actually very accessibly. So I would actually maybe start with this. This whole book is called Neural Networks and Deep Learning, and as you go through these, every time you read a longer form version of it, it'll make more and more sense, because like next time you encounter the terms dropout, you may not understand exactly why it's doing what it's doing, but you'll basically understand like the basic idea, right? And when you encounter term like the gradient, right, you kind of know, oh, it's the vector that represents the slope of the loss, and we're trying to optimize the loss so we can follow the gradient to the bottom of it. So things like this will kind of like help you become like wizards. Yeah. This question.
This might be like a little bit of a tangent, so feel free to tell me if we'll talk about it.
Sure.
So given what we've talked about how neural networks work, why is it that GPUs are commonly used to train neural networks?
Mm-hmm.
What about this process lends itself well to being done in parallel?
Yeah, good question. Actually, and that's actually very relevant to this, and I didn't include it, so good. I'm glad you asked that. So the question was, why? What about this process makes it so valuable? Makes it so relevant to GPUs, or so conducive to using GPUs instead of CPUs? Well, first of all, like, how many people here are familiar with the difference between CPUs and GPUs? Okay, most people. Just for those who are like unclear about it, most modern computers have two different categories of processors, a CPU and the GPU. CPU is your, computational processing unit or whatever? Central processing unit, oh, okay, yeah. And then GPU is graphics processing unit, which is a little bit of a misnomer because it doesn't necessarily have to be used for graphics, but it's typically used for graphics in most everyday tasks in computers. But the real difference between them is that CPUs are basically strong, like very fast, very high performance processors that you have only some small number of them in your computer. So you might have 4 or 8 or 16 or something, like a number of, and this gives you the number of threads. Like you might hear about threading. It's basically the number of simultaneous sequential operations that your computer can do. Now GPU is, instead of having some small number of like high performance processors, you have a large number relatively low performance processing units, which consume less power and so on. So then you might have like hundreds or thousands like of what are called GPU cores, right? Now GPUs are because you have so many of them, any task that can be inherently parallelized, like in other words, if you can break up a task into many different subtasks that don't necessarily have like conflicts between them, like they don't necessarily operate on the same data, and therefore have a danger into having collisions, like for example graphics, right? So when your computer is calculating what color should each pixel be at the same time, it can possibly do that independently of each other, and because there's millions of pixels on your screen. And so you can't just calculate each of the pixels of the CPU. It takes forever, right? Like 60 times per second. It's like a lot of processing. So that's why GPUs typically do the graphics. And that's why graphics programming is so weird, like with shaders, because you basically have to like make each pixel think individually, right? Now GPUs can also be used to optimize neural networks, right? It has nothing to do with graphics, ironically enough, right? And the reason is because when you do a forward pass, you can actually like take a layer, like all these neurons, right? Because let's maybe actually, I don't want to go backwards through that. Actually, let me do this real quick. So I'll go a little faster to show the visual. Oh, good. If we, where is it? So if you look at a neural network like this one, right, you can kind of see what's going on here. Like you can allocate a small number of pixels to each GPU core, and then have it calculate the gradient of those individually. And they don't depend on each other within a single layer. Like you can divide up a forward pass and the backwards pass into many GPU cores, which is complicated to program, but it can be done effectively, right? Matrices, basically, matrix math can be parallelized. And so that's why it turns out that we can actually, that it's much better to use GPUs because you can parallelize them. And that's very conducive to the stuff that that stuff. And that's kind of a big part of why, another big reason why deep learning has actually worked so well over these years is because, over these last few years, is because the advent of like relatively cheap GPUs that are all over the place means that we can actually like do this stuff a lot faster. Yeah?
So then is the consequence of that like rather than like when you're doing it on the GPU, rather than performing like the calculations for a layer like neuron by neuron, it's actually happening all at once as a big matrix calculation? Yeah. Okay.
Mm-hmm. Let me just get down to the bottom. There's just like 2 more slides here. Man, we're gonna need to do something about this because it's even worse than last week, right? Like I think. So yeah, so basically, if anyone's interested, like I highly encourage you, when I release the slides, you'll be able to grab these links, and that should make a lot more sense. And now finally, like this, I just posted this today. Like I hope now you can understand why this meme cracks me up. Like so everyone knows this, like the brain expansion meme, right? So you start with gradient descent, and you just become like more and more, sort of like obscene and ridiculous until, you're master of the universe if you can train a neural network in an initial guess. Like you're really. I should really stop preparing these so late at night, seriously. Like, okay, so we're ahead of schedule, which is really fantastic. So let's take a break now, and when we come back, we're gonna do some neural stuff. Okay. Okay, so for the next session, basically what I want to do is a continuation of what we started last week. I'm gonna show you some more applications, and almost everything that we're gonna show, I think maybe everything we're going to show, is an application of transfer learning, which we introduced last week. It's the idea that we can use big neural networks to train smaller neural networks that have some interesting tasks downstream. And actually, like next week, we're going to do even more transfer learning applications. Like a lot of this is kind of related to that. So just to recall, like transfer learning is all about using a trained neural network, which is already very good, has very good feature decomposition of some particular kind of data set. and then using that as the input to a smaller neural network. And the reason why we can get away with training a smaller neural network with a smaller number of data samples is because we're already getting very high quality information, right? Because neural networks require so much data because they try to learn a composition from scratch, right? A very, very detailed hierarchical, dense composition from scratch. And so this actually very much makes it a little easier to do that. So, and in the context of image processing, we use some image classification network, most likely that was trained in ImageNet, and we use that as a feature extractor. And we're going to use this term feature extraction quite a bit. So the stuff that I'm going to show you are connected to. We're actually going to focus, at least to begin with, on ML for OFX right now. And then I'll show you some of the demos that we kind of left behind last week, the ML5 demos. And I believe we did this before, but if you haven't already go to this link, ML4A-OFX, and then click on the, if you go to the ML4A-OFX, you'll find it on GitHub, and then you click on releases. And then just download the first thing at the top here, the ML4A-OFX modules. And so just download the ML4A-OFX.zip. And then if you want to do, there's one example in there that uses a Connect. So if you want to use some stuff, not today, but at some point you can download the OpenAI stuff as well. And that just goes into the, there's all the information is inside here. So basically, go into the, download this, please. You don't need to actually have to do this right now because I'm just going to do demonstrations right now. But for later, because I'm recording the lecture, you'll be able to recreate every single step that I do because I'm going to show everything from scratch. So from having downloaded this, you should eventually have basically this folder. And it's already getting slow, so I'm not optimistic about this. But let's see how it goes. You'll have this folder, and it has a whole bunch of applications inside that you can find. There it is. So that would look like that. And you'll have to just remember, run after you download, run this setup.sh file. So that means go into a terminal and run sh setup.sh. And what it does is just download some extra files and puts them into data. And then we're kind of good to go from there. So let me just quickly talk about the agenda. What we're going to do now is I'm going to show these examples, a few of these examples. So we're going to start with ML4A-OFX, and this is just a few nice interactive examples that can be the basis of applied projects. And so this is going to be kind of already getting us towards trying to make interesting applied projects. I'm going to show you ConvnetPredictor, ConvnetOSC, AudioClassifier, and DoodleClassifier. And then if we have some time, we'll go back to the ML4A demos that we missed from before. And I can actually, and let me get out of the slides now and we'll come back to them. So the first thing that I want to show you is ConvnetPredictor. And let's hope it runs. And oops, not that. Actually, let me just quickly exit the slides. So ConvnetPredictor is an Open Frameworks application that should just run for you. Once you've run the setup file, you can actually either right-click and click open or double-click. If you get something about it complaining where it can't find the model file, make sure that you actually have that ImageNet.SQLite file inside of data. This is all written in documentation, and otherwise, there's something wrong with the installation. They'll have to debug individually. But basically, ConvnetPredictor is an application that has an a trained image classification network inside of it that we use as a feature extractor to train some sort of a custom image classifier. And this is actually basically identical to the first demo that we showed last week, the ML4A demos. This is. Let's try it once, and then if not, then I'm going to take some contingency plans. Maybe we'll try to Yeah, well, it seems to be kind of working. It's just working slowly, but it seems that it will work for demonstration purposes. So ConvnetPredictor, this is basically the same thing as we did in ML4A demos. It will let you train a custom image classifier in a small amount of samples, and it's all going from the webcam, right? And then it lets you train multiple sliders or categories to react to this. So for example, if I want to learn a slider, let's say, I can add slider here, and now I have this thing that I'm trying to output, right? And this can take on any value. And we can think of this slider as controlling some parameter of some interaction that we want to develop. You know, whether it's in processing or in open frameworks or in touch design or in MaxMSP or one of the other many pieces of software that you guys use. And in general, if the software that you're using takes in OSC, Open Sound Control, how many people here are familiar with OSC? Okay, so like maybe half of you. For those who aren't familiar with OSC, OSC is basically like a data exchange format. It's very closely related to UDP, which is like network packets, but it's kind of designed to be like a more modern version of MIDI. And you might know MIDI as the standard format for musical devices to exchange information. Like all the jargon aside, what OSC basically allows us to do is to actually like share information between applications, and also share information between applications across a network. We're going to use it mostly locally, but it's just worth knowing that it makes it really easy to exchange like information between computers, right? What's nice about OSC is it lets us hook up different applications that aren't necessarily designed to work together. It lets us communicate with them, right? So like I have this ConvnetPredictor application, which lets us train an image classifier, and then what it does is that whenever it's doing its thing and it's predicting it's predicting the values of these sliders and categories, you can have it send that information to over OSC to whatever application that you happen to be coding for. So like if you're coding in processing, you can receive data from ConvnetPredictor. If you're coding in MaxMSP, you can receive data. And I think people are using all kinds of applications here, like including ones that I haven't mentioned. Maybe some people use Unity. Some people are, I don't know, like throw out like names of applications that you guys are using that do accept OSC. Which one?
Touch Designer.
Touch Designer, yeah.
Ableton.
Ableton, yeah. So Unity, yeah. So
how is the Unity OSC? Because I thought it's like a third-party plugin that's maybe not the best support. Have you tried it?
That's Ableton is like that too. Yeah, it's sort of like third-party plugin, but I'll actually show you an Ableton example later, provided that my computer doesn't explode. So anyhow, like I'm going to show you how to use this first. So the menu, like here, lets you. First of all, you can change the camera settings if you want. This is a little bit experimental, but it only makes sense if you have more devices. So if you have a second camera device, you can actually change which device it's pointing to by clicking here. And then the rest of the menu is the training menu. So we're going to train a classifier in much the same way that we did yesterday. And what I want to do is associate these images with a slider value. So like for example, if I'm going to put the slider value all the way to the bottom, let's say, or close to the bottom, 0.015. And what I'm going to do is I'm going to click record. And when I click record, this is just like the ML4A demos thing last week with ML5. When I click record, it's going to begin memorizing images and associating them with a slider value of that position. So like let's say I want it to be 0, roughly 0, whenever my phone is in front of the camera. So now I'm going to put my phone here, and I'm going to click record, and now it's going to begin recording samples. And you see it's going like it's going kind of slowly. It's going impressively fast actually. I was thinking that it was going to grind to a halt. But on your computer, it should work a little bit faster, like especially if you don't have it hooked up to a projector, as I do. So it's recording a bunch of examples, and usually for like a simple class, like maybe move it around to get some diversity in the samples, and then 30 or something like that should be roughly enough. Okay, so I'm going to click stop recording. And then once it stopped recording, I can maybe take this remote control, and I'm going to change the slider value to all the way to 1. Okay. Now I'm going to hit record, and now, oh, I shouldn't have done that. I got a few like random samples in there. I'll just compensate by kind of like giving some more samples. So remember, like, it'll start recording as soon as you hit record, and so like if you have irrelevant samples by accident, like it'll memorize those as well. So so that's just something to be aware of. So I get some remote control images. Okay, in general, it's like more or less making sense. And then I'll click stop. Okay. Now we have all this recorded data. If you ever want to start over, you can clear the training data. That's right here. And then the next thing that you would do is click train. And train is going to take all the samples that we gave it and fit a neural network to be able to predict the slider value as a result of the training data. And it should go actually quite quickly, generally speaking, because using a relatively simple model. We can change that internally, but basically it goes pretty quickly. So now once it's done, it says pipeline trained. I can hit predict. And now it's going to begin to control the slider automatically. So if I place my phone in front of it, right, as you recall, that should be a low value. It's going to go down. I probably didn't give it quite enough data, so you can see it's kind of... The other thing is it's actually lerping. So that's why it kind of goes slowly. So the prediction lerp smooths the slider. So that's why it's a little bit less responsive when you have a prediction lerp go up. Okay, but you see that we're roughly at the bottom, so if I put the remote in there, now it's going to move faster towards the top. Now it's really slow in my computer. Obviously, like, this should work a little bit quicker in yours. I don't know if anyone has it running already, but you should see that it's a little bit more reactive than what you're seeing there. What's cool is, like, we learned the remote control and the phone, and we can kind of like interpolate between them roughly, right? Like, so a little bit of phone goes down, but what if I have like a little bit of both? It's gonna fight. Yeah, it's gonna be like somewhere in the middle, right?
So in this case, it's kind of the confidence between the two, since you chose not a categorical thing.
Yeah, you could say it's sort of, it's like hedging its bets a little bit, right? It's a little bit of both classes, and so you get somewhere between the two. Okay, so like, what can we do with this? So here's the thing. Obviously, like, this, all ConvnetPredictor is set up to do is to just actually to just like to just do the classification, or sorry, do the regression. What we want to do is, let's say, get it into a third-party application. So what I'm going to do for that is I'm actually going to open processing, and that's going to take like 20 minutes to do, I think, because. So let's open up processing. There it is. Okay, processing. No, go up. Okay, let's open processing. Now the way I'm going to do this is I'm going to receive OSC from ConvnetPredictor. And, oh yeah. Now notice that here, while we're waiting for processing to load, notice the OSC settings at the bottom left. So the OSC settings tell us where it's going. So there's 3 settings to be aware of, and this is something that anyone who's used OSC should already, this is a review for you. If you haven't used OSC, the idea is that the IP tells you which network device to send it to. So localhost just means stay at this computer. Localhost is an alias also for 127.0.0.1, which just means my computer. You can simply change this to an IP address to another computer on the network if you wish to send information to them instead. So that's kind of cool, and that's something to be aware of, because later on there might be a lot of like creativity that we can come up with by sharing data between computers. We can create long chains, for example. This is something that I've wanted to integrate into classes, but I haven't been able to just yet. Then there's 2 more settings: the port and the message. The port is, like, again, this is a network setting, so like you can't have multiple applications listing in the same port, so just make sure you're using a free port, which, you know, like if you pick a random number, it should probably be free. Don't pick 22, because that's HTTP. And then, or SFTP, whatever. And then, and now, okay, so now we have processing loaded. And so what we want to do is we want to set up processing to receive OSC data from port 12,000. And the way that you can do that from processing is, first of all, you'll have to import the OSCP5 library. So if you don't have that, you can go to Sketch and then go to Import Library. This is really slow, man. This is just fast enough to do like a decent job, but we might have some holdups. Basically, like if you don't already have OSCP5, you would go to Import Library, and then you should have OSCP5 in there. If you notice, I have it down there at the bottom, OSCP5. If you don't have it, click on Add Library, and then search for OSCP5, and then add install, and then you'll have it. So that's just something really simple step to add a library. Now for our purposes, like the way that I always do this with processing is I actually will open the examples, because the OSCP5, like I always forget the syntax, you know, like how OSC is sent on processing, and so I like to open the generic example and then just simply copy and paste all of the relevant syntax and then receive on the other side. So I'm going to write a simple processing sketch to receive data from ConvnetPredictor. And I'm going to go down into the contributed libraries, and I have OSCP5 in here. And then I'm going to click on OSCP5 message, and I'm going to open this example. Okay, so now this is going to open OSCP5 message. This is just the basic sketch for sending and receiving OSC. Okay, and I can actually let's make it bigger. Now the way I always do this, I just copy the relevant parts, right? So we can go through this. How many people here have experience with processing, right? And how many people here have experience with P5? How many people here have experience with one or the other at least? Okay, like basically almost everybody. If you don't, then this might go a little quick for you, but don't worry, like I'll be here to help you out with it. And of course, like all your cohorts are here to help you as well, because of course this is very central to the class. So so like this, of course, just like P5, you have a setup method, you have a draw method, and you have these things that you want to have. You want to have these global variables. And so what I'm going to do is I'm going to copy the import statements and also the OSCP5 object. And then my remote location is only used if you want processing to send data. Now we're only receiving data, so we don't actually need that. So I'm just going to import the main OSCP5 object. I'm going to copy that, and then I'm going to place it into my new sketch and just kind of build things from scratch. Okay, so copy that. Now I'm going to create a setup method, void setup, void stop. And I'm going to make a canvas that, let's say, is like size 500 by 500 pixels. And now I'm going to instantiate the OSCP5 object. So the way you do that is you would go OSCP5 equals new OSCP5 this, and then this is very important, the port number. This has to, because we're going to receive, processing is going to receive data from ConvnetPredictor. And so we have to use the same port. Now if you look at ConvnetPredictor, it says, I'm going out on 12,000, port 12,000, with this message, /wec/outputs, and we'll get to the message in just a moment. But basically, we need this to match, so I'm going to say 12,000. And like we can go down a little further. We don't need the my remote address. That's, again, if you want processing to send to something else. And now I'm going to create a draw method. Okay. and it's going to do so painfully slowly. Okay, yeah. Void draw. Okay, now initially we won't draw anything. Now we want to look at this, and at the bottom of this, the example, you'll see that there's a built-in method called void OSC event. Now void OSC event is the name that you always have to use to create a function which will automatically be called every time the application receives an OSC message. So ConvnetPredictor is going to constantly send OSC messages, and if you have a function in your processing application listening on the correct port, which is called OSC event, and it's case sensitive, so make sure it's like capitalized, capital E, then it will be called automatically and given the message, and that's it. That's how we fetch the example, right? So what I'll do is I'm going to receive OSC event, OSC message. The example calls it the message. I've already mistyped this. I have a really it's like one of the awful things about this computer. Like my keyboard is failing, so the E key like doesn't work really well. So I'm committed to like not. I might give up. Like I don't know. Anyway, message. And basically, what we can do here is we're going to receive the message. I called it MSG because it's a little bit easier. And basically, this will be called automatically. Now, the thing that we want to be in the habit of doing is so a message has two parts. It has an actual like message string, which is from ConvnetPredictor's perspective, it's going to be /wec/outputs. And then it has some values attached to it. And that's how we transmit numbers. Now the message, like this address message, is used to like differentiate different kinds of messages from each other, because maybe you're sending multiple different categories of messages and you need to be able to route them, right? And so that's why you have this whole message thing. So what we're going to do is we're going to check if the message string is equal to the message string that ConvnetPredictor is sending. And that's going to be /wec/outputs. The reason, by the way, it's /wec/outputs is that ConvnetPredictor is by default designed to work with default messages that are the same in Wecinator. And so, and maybe later, depending on how well my computer does at this, I'll show you Wecinator. But we'll see kind of about that. So we need to check if the address is the same, and the way you do it in processing is a little funky. So just like you'll get used to it. It's an if statement, and so we go, okay, we'll grab message, which we receive as the argument into OSC event, and its message is given by the function addr_pattern. In general, like the syntax in the OSCP5 is really strange. Like it should just be message, I think. But anyway, like so it's hard to remember this. This is why I always like use the example. So anyway, if message.addr_pattern, and then here's another weird thing about processing in Java, string equality. If you want to measure if two strings are equal, you don't actually do it with double equals. What is going on here? Now it's really going off. It's like captured me at the most awkward. Yeah. Okay. Message.addr_pattern. So what I'll do is I'll do dot equals. This is how you do string equality in Java. It'll be /wec/inputs. Is that reasonably visible? I can make the I can make this a little bigger. Let's do like 24. Okay, so you do dot equals, and then basically now you can check. Now, if this happens, that means that we got the correct address. By the way, just notice that the slashes, these are actually like it's just a string. It doesn't. They don't mean anything. Like sometimes we have these slashes as convention in OSC addresses because we like to route things in like almost like a hierarchy. But it doesn't mean anything. It could be any string you want. So once we know that we've received the message, we can actually extract values from it. So I could do message.get 0. That will grab the first value that has been taken that has been taken from the like the message that has been put into the message. It's a float, so we do .get 0, and if it's a float, which it is because it's a slider, you would do .float value, and this will give you a float. So we could say like, okay, how about this? We'll create a value called slider, a float value called slider, and then we'll say slider equals message.get 0 float value, right? And now I can use that. So how about like we'll use it in a simple way. We'll draw the background, a color. Let's call that, and let's say the color is just equal to 255 times the slider, because the slider is going to give us a value between 0 and 1, right? And so if we multiply it by 255, you'll get a value between 0 and 255. Feed that into background, it'll change how light or dark the background is. So now if I run this, I'll run this application, and then I will also begin predicting. So I'll write, I'll hit predict, right? And as you recall, is it actually sending /wec/ oh, oops, I made a mistake here. It's not inputs, it's outputs. /wec/outputs. So this has got to match. Okay, so it's predicting as we speak. And as you can see, it's predicting white. If I put my phone there, black. Right? And actually, it's just doing white even if I don't have the remote. I think because of those errand samples that I put in the beginning. So that's white, black. You can see with the screen recording doing fine now. It's actually like much more responsive. So, and this is on an old laptop. So like for yours, it should be like even better. You can change the lerp setting if you'd like. So this will make it a little bit faster, but more jagged. Or actually, no, it's the other way around. This makes it slower. If we go all the way here, it'll be like automatic. Right? So more responsive, but less smooth. So I like to usually have the prediction lerp at like some small value. And this gives you a little bit more smoothness. So, okay, so that's the basic thing with ConvnetPredictor. And let's just kind of review. Like now, what you have is you have a way of getting image regression, regressing a slider to an image, receiving it inside of processing. And this is it. This is your basic template. This is all the code you need. It fits into the window. Now, what can you do with slider? Right? You can do lots of different kinds of things with slider, right? It doesn't have to be something really simple like doing the background. Like, what if we do something like this? I'm gonna show you my favorite, like my all-time favorite, like generative art sketch that you can do in like a few minutes. So what I'm gonna do is I'm gonna get rid of this background, and I'm going to say that we're gonna make a Bezier curve. So I'm gonna say float x1 is equal to width times noise. How many people know Perlin noise? Okay, named after Mr. Ken Perlin, who's here at NYU somewhere, right? And we'll give the noise value like something like we're going to create a new variable called t. Let's say float t. T is going to be equal to 0. And what we're going to do is we're going to make this be dependent on t. And we're going to use noise. Noise gives you a value between 0 and 1, so I'm multiplying it by width. So now we're going to have a value between 0 and width. And I'm going to have a little offset value. Now this is not going to make any sense, like I'm just doing random stuff, but this should make sense if you know how noise works. So I'm basically going to have 3 or 4 different noise values. I'm offsetting them in the second dimension so that they're not all identical. right? So something like this. And then I'm going to do the same thing for y, except it's going to be height times noise, and that's y1. And let's say that's 45. And now I'm going to do this 3 more times. So we got x2, x3, x4, y1 through y4. These are all different. And now we're going to draw a Bezier curve, which goes, which uses these values. So x1, y1, x2, y2, x3, y3, x4, y4. Now the addition of the this thing is making my computer bounce. I hope no one's getting like dizzy watching it. So finally, what we can do is, now this will just draw a Bezier curve on top of the screen. So like, okay, like let's, we'll do this in a second, but here's the trick. So what we're gonna do is we're gonna add slider to t. So t plus equals slider. So whatever value, all of these noise fields will be moving because t will continuously be incrementing, and it will be incrementing at a rate that's equal to the value of the slider. So if the slider is at 0, t is not going to move at all, and so the noise should be like roughly the same, right? So like, okay, let's actually try this.
Is that plus equals or times equals?
Plus equals, plus equals. Okay, so now you see that t is moving, and it's moving very quickly. If I put my phone in front of it, it'll move much slower, right? Because t is not moving that much. We can make this look a little nicer. So here's what I'll do. I'm going to first of all do like no fill, and we'll do stroke, we'll make it black with some transparency, and we'll clear the screen once in the beginning. We'll make it black. Oh, there goes the rain again. Okay, and let's try this again. I'm going to hit predict. So phone. Oh, it's black on black, of course. That's I got rid of ConvnetPredictor by accident. So you're going to have to open that again and retrain it.
When you do, when you save a model, in this example, how dependent on your initial conditions is that model? So like, if you went and had a different background or different lighting and tried to use the phone
it's somewhat sensitive to that.
Yeah.
Like, yeah.
So it wouldn't be very useful to save this model unless you're literally sitting right here and you haven't moved.
It's decent, like, but of course that will trip it up. Like, it tries to look for content, right?
Right.
I'm gonna re-record this, so for anyone who didn't remember how I did that, slider, 0, phone, gonna record a whole bunch of samples. So we're gonna get, like, let's say up to 30. You notice that it's actually going roughly the same speed as it was when my computer wasn't working. I think it's because it's actually using the CPU rather than the GPU. So, okay, so get some recorded samples. Now I'm going to move my remote control into here. Make a slider 1. So let's record a bunch of samples of this, and then I'm going to retrain it. You see that it's pretty quick. Like you can also save and load models. I didn't show how to do that. If you click save and load, it'll just save it internally. Okay, so stop. Now I'm going to hit train, and now I'm going to hit predict. Okay, so now 1, 0, and so on. So okay, now if I run this again, so growing very slowly, growing very quickly, slowly, quickly. Right, so like, okay, it's not like the most brilliant sketch in the world, but like the basic idea is that you have a way of making some parameter in your generative art sketch depend on something like an image, like a webcam stream. So that's pretty cool. Like you can do a lot of things with that. And the other nice thing is that you can have an arbitrary number of these. So if I can actually stop this, and I can stop, we can add a few more sliders. Like we can have 3 sliders if we want. So like I can make this one, this, and that, and record some images for, it'll train all 3 of them individually, right? So we could train 3 sliders, and then it's as easy as receiving them like this. So slider, 2 message, I get 1. Slider 3 would be message that get 2, and so on, right? So there you could train, and I'll leave that as an exercise. We won't actually do it right now, but basically you could retrieve multiple values by just simply adding sliders. Okay. So that's the basic idea with ConvnetPredictor and making, let's say, generative art or communicating with processing. I want to show you a slightly more advanced example now, while we have some time, which is that I want to show you how to use, let me just see, I wrote down the notes here. I'm going to show you how to use this with Ableton. How many people here are Ableton users? Okay, like 4 or 5 of you. That's actually like pretty decent amount. So I made this actually interoperable with Ableton, which is really cool. So you can control your
bass drop.
Yeah, exactly. So I'm going to show you how to do that. I'm going to leave processing open for now. And what I'm going to do is I'm going to open, and I'm actually, let's actually get out of ConvnetPredictor and restart it in a second. So I'm going to open Ableton. I just have a demo version of Ableton because I'm not a musician, really. I'm going to control Ableton with my mind, basically. No, with my camera. So let's make some. We're going to drop a bass. Exactly, that's what we're going to do. I'm going to go to the clips. I'm going to put in some. You guys pick. Like, tell me something that stands out. Reggaeton. Someone call that another thing. Excuse me. Dropping the beat. Give me another, like, what else? Someone call something out.
Can't read any of it.
Oh, you can't read it. Oh, that's right, yeah. Okay, fine. I'll just do hip-hop congos. Yeah. Okay, and then let's add like let's add 2 more audio tracks. And I'm gonna throw on some triplet hats. That sounds really weird, right? I don't like it. Kick drum. And the jazz break. Okay, you see, it's so easy to make music. It's like, now what I'm going to do is I'm going to put something on the, well, let's actually, we're clipping a little bit, so I'm going to turn it down. And I'm going to go to the audio effects. I'm going to go to the resonator. I'm going to put this Los Angeles resonator on it. Yeah. Okay. Groovy, right? Okay, so let's do something fun. What I'm going to do is I'm going to open up a program called Ableton. First of all, like if you guys using Ableton are doing this, you have to install something called Live OSC. You'll see in the ML for AOFX documentation it says how to do this, but there's a program called Live OSC, and then you'll have to enable it inside of your what is it, MIDI? Yeah, inside MIDI. You see how it's enabled here, Live OSC. So then you can open up another application inside of ML for AOFX called Ableton OSC. And now this has access to all of these parameters. So I'm gonna pick the tempo. Now I can control it from here. Now I'm also going to pick the master track, and see the Los Angeles filter shows up here. I'm going to pick the dry wet. Right, oh, I know it's not very visible for you guys, but there it is, right? Dry wet tempo. So now what I'm going to do is go back to ConvnetPredictor. Okay, we have this connection made. And now I'm going to like record again. So like I'll just do the same thing. So remote control, I'm gonna add 2 sliders now. These sliders now control these. see the correspondence? So that's cool, right? Now what I'm going to do is like, let's do this. Like we'll make it relatively fast and have a high dry wet. And I'm going to associate that with the remote control. So I'm going to click record. Okay, now I'm going to turn off the dry wet and make this even faster. My phone. Okay, now, that's pretty decent. I'm going to do one more thing. I'm going to turn this tempo really low. Yeah, sounds like my computer's not working, but that's actually just Ableton. Tempo really low. It's my dubstep. So now I'm going to record this with just me. So it's just like me in front of the camera. Sounds like King Tubby or something like that, right? Like, anyone know who that is? Anyway. So now I'm going to hit train. It's going to train both sliders individually, and now we can hit predict. Oh, I think I have a poor slider. There we go. It's not super reactive because, of course,
but you
like.
still have it on the same frame with that affected. Like it's,
What do you mean?
Like it's seeing both of them at the same time.
Well, no, my camera is only looking at this. Yeah. Oh, I mean, you mean if I do this? Yeah, exactly.
Yeah,
It'll
that's
be
what
somewhere
I'm saying.
between. Yeah.
Like it's gonna be
Yeah,
like
exactly. It will.
confused.
Yeah.
You can't train the sliders individually in this.
I actually don't have it. Like you can't arm one and not the other.
Yeah.
It's just like one of these things I didn't code, but like it should be
Theoretically, it would be
useful. Yeah, you can do it in Machinator. Okay, so you get the idea. It's not Mozart, but it is like it shows you how to create some interesting interactivity, right? So let me get out of Ableton. I'm gonna stop this, and now let's see. It's 2:40. I want to show you a couple more things. What I want to show you now is, so I want to show you DoodleClassifier, and I also want to show you AudioClassifier. So let's show you DoodleClassifier first, and let me just see, like DoodleClassifier, AudioClassifier, and then if we have some time, we can look at Wekinator and also ML-Fray demos. That stuff might get pushed a little bit to the side because in favor of time. But we do have enough time to. First of all, are there any questions like on what I just showed? I know it's like a rush through some of the technical stuff.
What was the Ableton live you saw to get that word? Live OSC?
Live OSC, yeah. If you look at the ML-Fray OFX like documentation, it says exactly like what you need to do. There's instructions on the release page for how to get that up and running. Is there a question here?
Yeah, to get a position of like an object that I train, how do I do like an X and Y?
It doesn't really do that exactly. Like you could train it for that purpose. You know, like okay, put it here, make it 0, then put it here, make it 0.5, and it would learn that to some degree. But it's not exactly like, that's not what it's just regressing the image, the features of the image, and it is location sensitive. So like, you know, you'll get some correspondence. So you could do that.
So training the X and then training the
Yeah,
Y.
but really, like if you're tracking the position of something, you want to use like normal computer vision techniques for that. Yeah. This is more like content aware. Any other questions? Okay, so here what I'm going to do now is I'm going to show you, let's do DoodleClassifier first, and then I'll show you AudioClassifier. And DoodleClassifier is actually like quite similar to ConvnetOSC, to ConvnetPredictor and ConvnetOSC, but it's kind of optimized to like basically work on doodles. So basically, if you open this, you'll get a screen that looks like this. And what I'm going to do is I'm going to, now normally the way that I would normally do this is I would actually have it pointing down. I just have a camera on my screen. Like normally you'd have an external camera looking down at some page, but I'm just going to do it this way, like, so this will be fine. So what I'm going to do, the whole point of DoodleClassifier is to train it. It's basically the same thing as ConvnetPredictor, except it can locate multiple objects, right? So like instead of having one image, one set of values, you can find additional, you can find multiple objects that are segmented using computer vision. Let me show you what I mean by that. So let's say I wanted to distinguish between circles, arrows, and stars. So I'm going to draw some stars on a page here. So I'm making like a few, I'm just drawing stars on this. Hang on, you'll see in just a moment. And basically you would have, you'd have your camera mounted. And if I put these on the screen, and if I have like the computer vision settings right, like you need to calibrate this a little bit. Like, okay, I need to maybe, where's the mouse? Okay. I need to change this so that, this is really actually quite difficult. I'm going to change this thresholding until it gets all of the stuff that I need and none of the stuff that I don't need. There we go. So it's finding the stars, roughly. There we go. So now I'm going to hit add samples. So there, it found these stars. Oh, I called them circle. Sorry, I have the name wrong. So these are called circle. So actually, fair enough. Like just remember the star is the circle. So now I'm going to change circle to star. Oh, that's confusing. Okay, just pretend circles and stars are circles. Okay, like obviously, like I've had my better days. Like. So I'm going to draw a bunch of circles, and the circles will be stars. Okay? You see I only drew 5 of them, right? So it's not even that many that you need. Okay, so here it's getting the circles in view. So now I'm going to hit add samples. Now it's got these as stars, right? And they're just circles, but we rename stars and circles. Okay? So the last one is going to be arrows of outrageous fortune. No one got that. Someone got that. Yeah, I hear some smirks. Okay, so arrows are going to be, I know it's hard to see, but like you pick the class right there. So arrow is going to be a bunch of arrows. Pretty straightforward. Okay, there's my arrows. Okay, so now I got a whole bunch of arrows, circles, and stars. The stars and circles are swapped. Now I'm going to hit train. It trains really quickly. And now I can actually like basically go, okay, I'm going to make an arbitrary circle and a star and an arrow. So I'm going to draw these. And what? What was I doing differently before? What? Wait, how did I do this before that I wasn't blocking it? I just was doing this, yeah. Alright, that's fine. Like, I'm just gonna... Oh, because... Okay, hang on. So now I'm gonna hit run. Or hit classify. Okay, so I put them, and you see it classified them. So the star is a circle, circle is a star, and then this is actually predicted wrong. So it says the arrow, it didn't get arrow right. I think because I drew all the arrows in a different orientation, so like it didn't get right facing arrows, but you get the basic idea. You can use this to to actually like classify things that you draw on a page. Now, why would you do that? Like, here's a good example of an application that you can make. I made this along with my collaborator Andreas Refsgaard. We basically made this installation called DoodleTunes. And I'm going to show you DoodleTunes. So basically, DoodleTunes is this application that lets you, it works with Ableton. So we trained it to recognize different musical instruments, and then it would trigger clips in Ableton. Right, so here's how it goes. That's Andreas. So this is just using DoodleClassifier. So he draws a piano and the drums. It's a little hard to see. There's a piano, drums, saxophone, and keyboard. So it starts playing all those instruments that you draw. There's a bass guitar.
These just clips in Ableton?
Yeah, exactly. Just the bass. Yeah. Right, so that's another cool thing. I'll just give you an example of another cool project. I think it's just linked on my Medium. So some students of mine at CIID used actually like a ConvnetClassifier. You could do this with Convnet with DoodleClassifier as well. But basically, this like you have a camera on top of a sandbox, and as you make patterns in the sand, it's continuously modifying these sliders and again playing Ableton. So you guys see what's going on? She draws in the sand, and then it changes the sound. Just whatever they trained a whole bunch of shapes and then associated with sliders. And it stops. Right. So this kind of thing, also very, very much in the spirit of what's possible. So you can see there's a whole lot of interactions that can be built from these two applications, like DoodleClassifier, ConvnetPredictor. How many people here code in open frameworks a little bit? Okay, a handful of you. For those of you who do, you're in a really good position because you can actually just modify the applications directly and you can combine them with other things that you do in open frameworks. If you don't, though, you can just use them as an OSC transmitting device, right? So that's kind of like another option for using it and then put it into the environment that you want. But the whole point is that these can be used to trigger, to sort of trigger interactions, right? And that's kind of like the goal. Yeah?
Do you know if anyone has like tried to modify the DoodleClassifier app to also keep like track of the spatial position of where the classified shapes are?
Wait, say that again? Like
to have not just like, is this here, but like where on the page is it?
The thing is, like, if you really think about what's happening, like, you wouldn't use probably normal computer vision techniques to track the location of objects. You could do it with ConvnetClassifier, like, because, you know, you can train it to predict 0 when it's at 0 and predict 0.5 when it's halfway and predict 1. But it's sort of like not doing that exactly. It's really trying to identify the image. And so, like, if you're really just trying to do object tracking, you should just use, like, normal object detection means or computer vision techniques for that.
Yeah, I guess I mean like combining the two approaches, like having both object detection and then like classification of individual type objects.
Well, that's what DoodleClassifier basically is. Yeah. And DoodleClassifier, like, the funny thing is, like, we designed it with doodles in mind, but you could do it with other kinds of objects, like the camera's pointing downward and you can have rocks. You know, like, it'll find them. So there's no reason that it has to be for doodles, even though it's called that. Like, we've had students use it for other things too. And then that does that. Basically, it finds the individual objects and classifies them. And right now in the OSC, it doesn't give you the XY position, but it could just as easily, right? Like it just, that has to be put into the Open Frameworks app. So there's that. You could do that. So this section of the video is actually being spliced in. We had a little problem with my audio card when I tried to introduce AudioClassifier earlier today, so I decided to just scrap the original video and just interject this in. So I'm going to do a section on how to use AudioClassifier and then return to the normal class video after that. So AudioClassifier is basically the same thing as ConvnetClassifier, except it works on audio. So it can do basically like feature extraction audio and then classification based on the kinds of sounds you make. It's a pretty simple app, and it doesn't really have very much capacity to work on like sort of time-based sounds, things that have some sort of a, like let's say words, but it gets pretty good at capturing timbre. And so what I'm going to do is I'm going to record, so this is AudioClassifier, and you'll see in the ML4OFX collection. The interface is quite similar to ConvnetPredictor, except that you just see audio here. So this is measuring the volume. This is measuring the MFCCs, that's mel frequency cepstral coefficients. These are very standard standard digital signal processing features that are used for characterizing audio. We're extracting them from each of the frames, audio frames, in real time. So basically, this is our feature vector right here, the average and also the standard deviations of these bars. So basically, I'm going to record 4 different classes, and then we're going to try to use them in an interesting way, and also try to get that into processing. The first thing that I want to record, which is going to be associated with class label 1, is just going to be silence. So as soon as I hit record, it's going to begin to record the sound coming from the microphone, which is going to be mostly silence, maybe a little bit of background noise. And then that's going to be associated with class label 1. So I'm going to go ahead and hit record. Okay, you see we got a whole bunch of samples in there. Now I'm going to, so silence is class label 1. Class label 2, I'm going to do something a little silly and a little embarrassing. I'm going to ooh at the microphone. So well, let's just do that, right? So class label 2, I'm going to start oohing and then click record, because I don't want to get errant frames that have no content or irrelevant content in there. It has to be recording the exact thing that I want to be associated with class label 2. So on the count of 3, I start oohing and I'll hit record. 1, 2, 3. Ooh. Okay, so class label 3, I'm going to do the same thing, except I'm going to ah instead of ooh. So on the count of 3, 1, 2, 3. Okay, very embarrassing. And then class label 4 is going to be me clapping. And for class label 4, I'm actually going to turn on threshold mode. And you'll see this red bar pop up. And threshold mode, it only actually triggers a sample to be recorded when the volume goes above the threshold. And then only triggers the next one after it goes below. So let's see, if I clap, let's get that down just a little bit lower. I think maybe let's say to there. Okay, so now when I start clapping, it's going to begin to record class label 4 and associate those with the claps. So here we go. Okay, cool. So we got 4 of these trained. So now I'm going to hit train, and it starts to predict. So now, first of all, it's in threshold mode, so if I clap, it should predict a 4. Okay, cool. And then if I turn off threshold mode, I should be able to do our silences and our oohs and our ahs. So I'll turn that off. Not so well. Okay, so it's not doing so well with silence. Okay. Ooh, ah, ooh, ah, ooh. Okay, so we're not getting class label 1 very well, but it's good enough for the purposes of this demo. So let's see what we can do with this. I'm going to turn threshold mode back on, and I'm going to open another another application in the collection here called Keyboard OSC. Actually, before I do that, I want to show transmitting this to processing. Right? So in processing, we can, this is the original processing example that I used to capture the slide. What I'm going to do now is actually, instead of receiving a float, we're actually going to be, we'll still be receiving a float, but now we want to turn it into a class label. So let's say that we turn this into a class label. We'll say int c, and we'll get rid of all this t and slider stuff. So there's no t. We're just going to erase this. And so we're just doing a simple thing, which is receiving c. Now, because this is a float and we're getting an integer, we need to cast it into an integer. So we can do that like so. Okay, so then once we have that, we can say, okay, if c equals, let's say, like, okay, if c equals 4, we can just say we received the clap. So that should be the label that we get. So if I run this, it should now be receiving, and oh, and actually it won't be receiving this right away because we have to match this, right? So this is now going to port 9000 rather than 12,000, and it's receiving the address /classification. Right? So make sure that you match the OSC. So I go ahead and run that, and now we should be able to receive claps. Okay, invocation target. Okay, this means that I think we're actually receiving it wrong. It should just be an integer most likely. So let's try that. We received the clap. And you can kind of see that there. Okay, so that's pretty cool. So we can get audio events to show up in processing. What else can we do with this? Can we do something more interesting? So I'm going to open up an application called Keyboard OSC. And what Keyboard OSC is going to do is going to let me control my keyboard while it's from receiving OSC from here. So I'm actually just going to turn off predicting for just a second and go back to Keyboard OSC, and we can go ahead and change the settings. And we'll say that, okay, for number 1 we'll do nothing, so that's going to be pass. For when we get receive class label 2, we'll do left. Class label 3 will go right. And this is the important one. 4 I'm going to associate with the spacebar. So now this is going to send its classifications to Keyboard OSC, and when we have allow keyboard simulation, it's going to and this is predicting, it's going to actually do these keyboard events, right? So here's what I'm going to do. I'm going to allow keyboard simulation. I'm going to hit predicting, and now we're going to do the T-Rex game. So here's how this is going to work. I've done this at a lot of workshops. Oh. So here's how it's going to go. All right, here we go. You get the idea. So I'm not so good at this, but let's see how far I can go. Well, it's just me. Okay, it's not amazing stuff, but it's fun enough, right? So I'm gonna turn off predicting. Okay, so let me just show you the last couple slides. So basically, okay, like this is what we got through. I'm gonna do the audio classifier separately. We didn't get to do Wekinator demos right now, but again, like that's something that maybe I'll punt to the next week. And then I'll also I'll show you the PostNet demos at some point also. And lastly, let's just see. So like a few things that might come up, like why use ML5 versus using Wekinator versus using ML for AOFX stuff, because you see they overlap quite significantly. And there's really, you know, like most of the time they can all do the things that you want them to do, but generally speaking, ML5, you know, along with P5 is a little bit more optimized towards web stuff. So like if you want to do web stuff, then those are a little bit better. ConvnetPredictor and then Wekinator are also cross-functional because they both implement a neural network. You can use them, both of them can be used for like desktop applications, right? So if you want to make an installation or something, it's going to be ideal for that. But mostly, like, they're all kind of cross-functional. So like most of the things that you want to try to do, you could do with any of them. So it's good to just get like a little comfortable with all of them because you might see that, you know, some are more optimized for some use cases rather than others. Now, next week what we're going to do is we're going to actually get to some more low-level applications of neural networks. We're actually going to do stuff with Python. Like, that's going to be our introduction to Python stuff. And we're going to introduce like core information retrieval tasks. So things like basically like being able to do nearest neighbor image search. And then from that, there's a lot of like additional applications that kind of grow out of that. So we'll talk about TSNE and data visualization stuff next week as well, and show like a few more like data science-y type applications. And that will really sort of take us through the end of the first module, and we'll kind of talk about how we'll proceed from there. Like in October, we'll kind of get into doing more generative stuff. Are there any questions? Okay, cool. So let's call it a day, and next week we'll try to get these like technical considerations a little more stable, and then we'll kind of continue on this path. Okay, see you next week, guys.